With this lesson, we finish the first part of the course of probability. The first topic that we discuss in this lesson is related to the odds of a binary event, and after that we will deal with many interesting examples. First of all, let me tell you that a binary event is an event that can have only two possible outcomes. For example, success, failure, true or false, yes or no, 1 or 0, etc., etc. Typical examples of binary events are coin toss, because the outcome can be either heads or tails. Pass-fail test, because a student can either pass or fail an exam. There are no other options. A light switch can be either on or off, and things like that. Instead, a typical example of a non-binary event is rolling a die, because there are 6 possible outcomes from 1 to 6. Given a binary event E, its odds ratio is the fraction between the probability of occurrence and that of non-occurrence, that is, either P of E divided by P of the complementary of E, or P of E divided by 1 minus P of E. If the numerator is larger than the denominator, then we say that the odds are O of E to 1 in favor of the event to occur. Vice versa, we say that the odds are O of E to 1 in favor of the event not to occur. And if the odds ratio is 1, then we say that the odds of E are 50-50. In fact, in this case, the probability of occurrence of E matches the probability of non-occurrence. The use of odds is very common in bookmakers. Now let's use Bayes' theorem in order to reformulate the concept of odds ratio. Consider another event F which may affect the event E, and then write the Bayes' theorem for E and its complementary. After the occurrence of the event F, the odds ratio O of E is updated as follows. We have to write O of E given F as the fraction between the conditional probability of E given F divided by the conditional probability of the complementary of E given F. Thanks to Bayes' theorem, we can rewrite this conditional probability like this. Thanks to this other instance of Bayes' theorem, we can rewrite this conditional probability like this. We see that the prior probabilities of f can be cancelled, and we remain with this expression, in which we can see the original odds ratio, and so the updated odds ratio can be written as the original odds ratio times this coefficient here, which is called the Bayes factor. Clearly, since we have a direct proportionality, we have that the higher the Bayes factor, the larger the odds ratio in favor of E after the event F, and of course vice versa.
We have just encountered another example of peculiar language in probability with the concept of odds of a binary event. A binary event may just happen or not happen. For example, imagine to be an actor and to be nominated for the Oscar. In this case, the binary event is either you win or you don't win the Oscar. Mathematically speaking, the odds of a binary event is simply defined by the fraction between the probability that E occurs and the probability that its complementary set occurs. Stated equivalently, it's the fraction between the probability that E occurs and the probability that E doesn't occur. By definition of odds, it's clear that if the odds of the event E are 1, then E has 50-50 chance to happen. Instead, if the odds are greater than 1, then E has a greater chance to occur. Instead, if the ratio is smaller than 1, then the odds are in favor of E not to occur. Finally, we have seen that we can update the odds ratio thanks to the concept of conditional probability and Bayes' theorem. We have seen that the odds of E after the event F occurs is the product of the original odds of E times the so-called base factor that you can see written here.
In the next page, we're going to discuss a very interesting example in which we use the odds ratio and the base factor. Let's read together the quite famous example of the left-handed criminal. A police investigation has determined that the perpetrator of a criminal act is left-handed. There is a person suspected for the crime who is indeed left-handed. Knowing that left-handed people are 10% of the population, determine how much the ratio favorable to the suspect's guilt increases. We're going to see in the analysis of this example and the following ones that the key to solve a problem of probability is to define the correct events. The first event that we define is the event E, which is the binary event, the suspect is guilty. Of course, it is a binary event because either the suspect is guilty or not. The second event, F, is the criminal is left-handed. We want to determine the base ratio, so we need the conditional probabilities. First of all, we notice that the conditional probability of the event F given the event E is 100%. To understand why, let's follow these arrows. Imagine that E occurs, then the suspect is guilty, which means that the suspect becomes the criminal. But since the suspect is left-handed and the suspect is the criminal, this means that the criminal is left-handed. And this is exactly the event F. So if E occurs in a deterministic way, we arrive to F. That is, the probability of F given E is 100%. Instead, what is the conditional probability of F given the complementary of C? Well, the complementary of C is the fact that the suspect is not guilty. This means that the criminal is still unknown, and we have just the information that the criminal is left-handed, whose probability is 10%. So, in this case, the conditional probability of F given the complementary of C is 0.1. In other words, the occurrence of the complementary of E doesn't have any influence on the occurrence of F. And this is the reason why the conditional probability is exactly the same as the prior probability that the criminal is left-handed, which is 0.1. Let's now compute the base factor, which is the conditional probability of F given E divided by the conditional probability of F given the complementary of E. That is 1 divided by 0.1, which is 10. The take-home message is that discovering a relatively rare feature in common between the criminal and the suspect increases a lot the probability that the suspect is indeed a criminal. And of course, the rarer the feature, the higher the rising probability. Having discussed the odds ratio, the base factor, and an example related to this concept, we can now go for 4 very interesting examples in which we will use Bayesian inference in order to understand how to solve problems. The first example we deal with is very famous and it's called in the literature the rare disease problem. It's a very important one. Let's read it together. A person tested positive to a very rare disease which affects the 0.1% of the world population. The person asks the doctor about the accuracy of the test, and it turns out that it correctly identifies the 99% of people who have the disease. What is the probability that the person actually has the rare disease? As a related problem, it is asked to update the probability in the case that the person repeats the test in another lab and turns out to be positive again. Using the mathematical language of probability, we have that the answer to the first question is the conditional probability that the person actually has the disease after being tested positive. So we need to define the following 2 events. The first event, usually indicated with the letter H, is the hypothesis that the person actually has the disease. This event occurs when the hypothesis is true. The second event, in general indicated with the letter E, is the fact that the person has tested positive. Thanks to the generalized Bayes theorem, we have that the conditional probability of the hypothesis being true given that the event occurs is this one here, and this is exactly the probability to actually have the disease given that the test turned out to be positive. So you see that in order to solve the problem, we need a bunch of probabilities. P of H is the prior probability that the hypothesis is true. That is, the probability that the person had the disease before testing positive. P of the complementary of H is, of course, the probability that the person does not have the disease. P of E is the probability of testing positive, and this conditional probability is the one related to test positive given that the person actually has the disease. Finally, we have this conditional probability, which is very interesting and important. In fact, if you think about it for a second, it is the probability to test positive given that the person doesn't have the disease. This case is said to define a false positive. In general, the prior probability P of H is the most difficult one to find. In many cases, P of H is nothing more than an educated guess. However, in this particular case, a reasonable approximation of P of H is the probability of the disease in the whole population, which we know is 0.1%, that is 0.001. Moreover, we have the information about the test accuracy, which is 99%, that is 0.99. In general, the accuracy is used to approximate this conditional probability here. Using these approximations, we can compute the conditional probability of H given E as follows. Replacing all the values that we have, we obtain around 0.09, which is 9%. I am pretty sure that this result is very counterintuitive for the majority of you because of the high accuracy of the test. However, I'm going to show you that if we think about the computation from a different angle, we can realize that this result is actually to be expected. Consider a population of 1,000 people. Then the probability that a person is affected by this rare disease is 0.1% of 1,000, which is exactly one person. Let's suppose that this is indeed the case. That is, exactly one person is ill and there are 999 people who aren't. We know that the test correctly identifies 99% of cases, so there remains 1% of false positive, that is 10 false positive. To resume, the situation is the following. We have 11 positive tests with 1 true ill person and 10 healthy people. With this data, we can compute the probability of being ill after being tested positive as 1 divided by 11, which is around 0.09, that is 9%. So you see that what we obtain now is exactly the result of the previous calculation. The very important take-home message is that an accurate test is not necessarily a good predictive one, in particular for very rare diseases. However, there is a catch. In fact, suppose that the person undergoes another test in a different lab and turns out to be positive again. This time, the prior probability P of H must be updated. In fact, this time the person arrives to the second lab with the result of the first test being positive, so the prior probability must be updated to this value. If we perform the computation, this time we obtain around 0.91, that is 91%. So we see a dramatic increase in the probability, and this explains why, when of course it's possible, we must run tests in different labs in order to strongly reduce the cases of false positives. The next example that we discuss is called the cookies problem. Alice and Bob are a young couple and they both receive as a gift a box of cookies. In Alex's box there are 15 chocolate chip cookies and 5 vanilla ones. In Bob's box there are 8 chocolate chip cookies and 12 lemon curd ones. By mistake, the boxes are mixed and one of their friends eats a chocolate chip cookie. What is the probability that this one belongs to Alice's box? Of course, we expect to find a probability larger than 50% because of the presence of more chocolate chip cookies in Alice's box. However, to quantify this value, we need to use Bayes' theorem. The elements of the problem are the following. The sample space S is given by the 40 cookies belonging in the two boxes. Then we have the events E and F, which are the fact that a cookie belongs to Alice's box or Bob's box, respectively. Finally, we have the event C, that is, a cookie in one box is a chocolate chip one. If we apply Bayes' theorem, we have that the probability that the friend ate a chocolate chip cookie which came from Alice's box is given by this formula here. Of course, the prior probability that a cookie belongs either to Alice or Bob's box is identical, and so we have that P of E and P of F are exactly equal to 1/2. Moreover, since there's a total of 15 plus 8, that is 23 chocolate chip cookies, the probability to eat one of them is given by 23 divided by 40. Finally, since there are 15 chocolate chip cookies in Alice's box, we have that the conditional probability of C given E is 15 divided by 20, that is 3 divided by 4. If we introduce the values that we have just found in Bayes' theorem, we obtain around 65% of probability that the chocolate chip cookie came from Alice's box. The next example is the kittens problem. A female cat just gave birth to 2 kittens and one of them is a male. What's the probability that also the other cat is a male, given that the average probability to give birth to a male among cats is 50%? Our intuition leads us to think that there is a 50% chance that also the other kitten is a male. However, we are dealing with a conditional probability because the female cat already gave birth to a male, and so we must carefully formulate and solve the problem using Bayes' theorem. As in the previous example, the first thing to do is to identify the sample space. For the present problem, S is given by the 4 possible couples of female-male kitten, in the sense that the female cat can give birth first to a female and then to another female, first to a female and then to a male, first to a male then a female, and finally first to a male and then a male. Then we define the event E, that is, at least one of the kittens is a male. Finally, we see that the probability that we are searching for is given by this conditional probability here. That is the probability of having 2 male kittens given that one of them was already born. By Bayes' theorem, we know that this probability is given by this formula. Since the birth of males or females in cats happens with the same frequency, we have that this probability is 1/4. Why that? Well, because this is simply an outcome, this one here, of a sample space which contains 4 outcomes. These outcomes are equally likely, and so we have that this probability is just 1/4. Now let's consider what we have called the likeliness. This is the probability that at least one of the kittens is male, given that both kittens are male, but this is of course 1. The last probability that we must compute is the so-called marginal, that is P of E. In order to compute that, we can use the law of total probability. Recall that this law is represented by this formula here. In our case, it is convenient to take as the event F the couple of 2 males. If we rewrite the law of total probability using this choice, we obtain this formula here. Why taking F to be the couple of 2 male kittens was a smart choice? Well, because we already know that the probability of having 2 male kittens is 1/4. So the probability of the complementary is 3 divided by 4. And finally, to compute this conditional probability, we note that the complementary of MM is given by this set of couples. So we see that there are 2 chances over 3 that the event E occurs. Recalling that the event E is at least one of the kitten is a male. And you can see that in these couples we have at least a male. For this reason, this probability is 2/3. To conclude, using all the values that we have found, we can calculate the probability that the female cat gives birth to a second male as 33%. Again, we see that our intuition is deceiving when we deal with conditional probabilities. The last example that we discuss is called Murder, She Wrote, exactly as the famous TV series from 1980s. A person with a 0 blood type is arrested by the police as a suspect for a murder. On the murder scene, the famous writer, murder solver, and also curse bringer Jessica Fletcher finds 2 blood traces not belonging to the victim. Once analyzed, one of them is found to be of type 0 and the other is found to be of type AB. Knowing that 60% of people have 0 blood type and only 1% of people have AB blood type, establish if the novel information gathered by Jessica Fletcher raises or lowers the probability that the person arrested by the police is the actual murderer. First of all, we remark that the suspect is either guilty or not, and of course this is a binary event. Hence, the increase or decrease in probability can be quantified through Bayes factor. As we have seen in the previous examples, the most important thing to do is to establish the pertinent events for the problem. Let's start with the event E, that is, the suspect has left a trace of his blood on the murder scene. Then we have the event Z, that is, blood traces of type 0 are found at the murder scene, and the event small ab, that is, blood traces of type AB are found at the murder scene. Since both Z and AB occur because they are found by Jessica Fletcher as blood traces, we have to consider the intersection between these 2 events, and the Bayes factor is this one here. Let's analyze the probability of the intersection between Z and AB given that E occurs. First of all, notice that the probability of Z given E is 1. Because if E occurs, that is, the suspect left traces of his blood at the murder scene, since the suspect has 0 type blood, then Z occurs. So you see that the occurrence of the event E implies the occurrence of the event Z. There is nothing probabilistic in that. So the inference from E to Z is deterministic, and the probability must be 100%. Now imagine that E occurs and both traces of blood of type 0 and AB are found, that is, Z intersected with AB occurs. However, since the suspect has 0 blood type, the occurrence of E has absolutely no influence on the event AB. In other words, E and AB are independent events. We know that when we have independent events, we can factor out the probabilities of the single events. So this probability can be written as the product of the probability of Z given E times the probability of AB given E. We have already seen that this probability is 1, and regarding this other probability, we can say that it is exactly the probability of AB, because E doesn't have any influence on the occurrence of AB, right? But what's the probability of AB? Well, as we have said at the beginning, the probability of having blood type AB is 1%, that is 0.01. To conclude, this probability, which is the numerator of the base factor, is 0.01. Now we have to compute the denominator of the base factor, that is, the conditional probability that Z intersected with AB occurs, given that the complementary of E occurs. The complementary event of E is that the suspect didn't leave any trace of his blood on the murder scene. In this situation, the fact of finding two types of blood traces must be ascribed to two other persons. One of these persons must have blood type 0 with probability 0.6, and the other must have type AB with probability 0.01. So this probability is this product plus this product another time, that is 2 times this product, which gives 0.012. To conclude, if we use this value for the numerator and this value for the denominator, we find that the base factor is given by 0.8, which is less than 1. And so the interpretation is that the probability that the suspect is indeed guilty has lessened after the discovery of the two blood traces. The main reason for the decreasing being that the blood type AB is rare. We have finished discussing the first chapter of the notes. For you, it's the right moment to stop and try to answer all the questions that I have collected here, which refer to the most important concepts that we have analyzed in the first chapter. As always, I strongly encourage you to test each other, and whenever you have doubts or simply you don't feel very confident about a topic, you should go back to that topic either in the notes or by rewatching the corresponding video using the subdivision in chapters which I made to facilitate this task.